Natural Language Processing by Gail, Kenya, Amanda, Tracy, and Michael. Why is natural language processing important? Natural language processing promises to reduce costs and improve quality for healthcare providers. By processing text directly with computer applications, an organization can leverage the wealth of available patient information in clinical documentation to improve communication between caregivers, reduce the cost of working with clinical documentation, and automate the coding and documentation improvement process. We will cover 5 different applications of natural language processing in this slideshow. The first will be information extraction, followed by information retrieval, text generation, user interfaces, and machine translation. Information extraction. The definition of information extraction is to pull needed data and information from narratives, free text, and data banks, and to put that into a structured, readable format. Information extraction is also referred to as knowledge extraction, information extraction, and text extraction. This topic is closely related to data or text mining. How does information extraction work? Extraction can work in many different ways, and often obeys rules and/or statistics in order to deliver the best precision and recall for users. One example of the set of algorithms might be recall equals true positives divided by true positives plus false negatives, or precision equals true positives divided by true positives plus false positives. How is it used? In the biomedical world, information extraction tools are used in multiple ways. Many systems, such as 3M Health Information Systems 360 and Compass, and Health Fidelity's Reveal version 2.0, work inside existing EMRs to pull keywords and data from both patient and clinician narrative text. Clinicians can also use information extraction tools to pull relevant academic literature from large databases, which saves time and improves recall and precision. Researchers can also save time and costs by using information extraction tools to pull needed data from large data sets, which can help establish patterns and trends. These are just a few of the ways that information extraction can aid clinicians and researchers in the biomedical field. Research on information extraction. The Mayo Clinic study examines the development, features, and technology in the Mayo Clinic's open-source natural language processing software called Clinical Text Analysis and Knowledge Extraction System, abbreviated as CTAKES. The software focuses on extracting free text information using open-source natural language processing terminologies, such as Unstructured Information Management Application Framework, to better support clinical research. Meanwhile, Maestro and Hoag's study examines how effective different natural language processing tools are when extracting information about medical problems from patient narratives. Evaluating current research literature on the effectiveness of text extraction within different EMRs can help healthcare providers and organizations decide what their needs are and what types of systems will work for them. So, without information extraction systems and tools, natural language processing would not exist. It is critical to have the ability to pull the right information in order to find trends, establish and predict patterns, and aggregate data to create information, which then leads to knowledge. Many presentations have been given on this topic at a variety of conferences and meetings. Here are just 2 examples of presentations. The first one is from the Wolf-Ram Data Symposium, and the second was a graduate student presentation at the University of Japan. Many academic and medical institutions and associations have natural language processing groups which conduct research and experiments on information extraction tools. Many commercial and research companies have been working on software products to incorporate into EMR systems. Here are 2 of the most recent products to hit the market. Information retrieval. Here is just one example of the type of information retrieval resource you can find. How does information retrieval work? In very rough terms, a basic text retrieval system consists of three separate files. The file full of records or full-text documents, including bibliographic and indexing information. The dictionary, which is an alphabetical list of all the unique words in the database. And an inversion list, which stores all the locations of occurrences for each word in the dictionary. This structure is called an inverted file. Searching very large databases is efficient with the file structure, since each word in the dictionary is an entry point for beginning a search. Steps in information retrieval. Step 1 is document processing, where documents are input into the system. Step 2 is query processing. When a query comes in, it must be interpreted by the system. Step 3 is query matching. The interpreted query is matched against the inverted file and the knowledge base if there is one. Step 4 is ranking and sorting. Once all the candidate documents are selected that match the query, they are sorted by date, by field, or by how relevant the document is predicted to be by the query. Here is a diagram depicting the current processes of clinical information retrieval versus those proposed in the design of automated retrieval consoles. Here are a few YouTube videos about information retrieval by Dan Jawofsky and Chris Manning. Natural language generation. Two definitions of natural language generation that have stood the test of time are provided here, each with their own emphasis. McDonald's 1987 definition: natural language generation is the process of deliberately constructing a natural language text in order to meet specified communicative goals. Very succinctly emphasizes the deliberate construction of text rather than just standalone sentences. Reiter and Dale, two preeminent researchers in the field, published a definition with a slightly different emphasis about a decade later. Natural language generation is the subfield of artificial intelligence and computational linguistics that is concerned with the construction of computer systems that can produce understandable texts in human languages from some underlying non-linguistic representation of information. Their emphasis is on underlying non-linguistic representations that are used as input data. Natural language generation is recognized as typically having three sequential processing stages, moving from the general to the specific. In other words, each stage refines the output created by the preceding stage. The first stage is document planning. The document planner determines what information will be communicated in text. Another term for this is content determination, and how the document will be organized. Another term for this is content structuring. The output of the document planning process is the document plan. This is what is used as input in the next stage, microplanning. The second stage is microplanning, which is also known as sentence planning. The microplanner determines how the information will be linguistically stated in generated text. So, it is in this stage that information is divided into individual sentences and paragraphs, and the elements that are used to make the text cohesive are selected. The output of this microplanning process is a set of sentence plans. The third stage is realization. The linguistic realizer generates actual output or surface-level natural language text, based on the document plan and the sentence plans. This is accomplished with the use of grammars, also known as grammar rules, that specify how a sentence is to be formed. A specific set of grammar rules is associated with every natural language. Natural language generation output evaluations. How well does any given natural language text generation application perform? The evaluation of text output can be measured a number of different ways, but generally speaking, the output is measured against some standard or metric. Here we present the three basic accepted techniques for the evaluation of natural language generation systems. Extrinsic evaluation. This approach measures how effective the natural language generation system is at achieving the goal that it was intended to communicate through the generated text. So, for example, a system which generates letters to smokers based upon their responses to questionnaires can be evaluated by measuring how many smokers stopped smoking. Extrinsic evaluation is generally the most trusted evaluation, but also the most expensive. Human evaluation. Human evaluations are more appropriate for projects that are smaller and cheaper than larger budget projects that can afford extrinsic evaluations. Here, the system's output is evaluated by asking human subjects to rate the text's usefulness using some ordinal scale. Metric-based evaluation. This approach compares the natural language generation system's output text to the text written by humans who have access to the same system input data and communicative goal. Our research has revealed 2 companies that specialize solely in creating applications using natural language text generation. One company is called Data to Text. This company is a spin-off from the Natural Language Generation Laboratories at the University of Aberdeen in Aberdeen, Scotland. The staff includes a mood writer, a leading researcher in natural language generation. Data to Text case studies include a project called Baby Talk, which generates summaries of clinical data about babies in neonatal intensive care units. Another company is called CoGenText and is located in Ithaca, New York. According to their website, the company focuses particularly on web-based applications. A solution listed in their portfolio, FOG, is referenced a lot in the natural language generation literature. As part of a Canadian product called Forecaster's Production Assistant, FOG generates textual weather reports in English and in French. We found only one natural language generation dedicated textbook, Building Natural Language Generation Systems, that was written by a mood writer and Robert Dale in 2000, with a later edition printed in 2006. The 2000 edition has been cited over 800 times according to Google Scholar. A review of the book by Wilson in 2003 states that those interested in exploring the synergies and limitations of natural language processing and user molding will find this book an indispensable guide. And students, academics, and researchers and developers seeking a single source foundation for already fielded natural language generation systems, as well as research and development systems, will find it in this book. There is one special interest group called the Special Interest Group on Natural Language Generation that falls under the umbrella of the Association for Computational Linguistics. The group provides a forum for the discussion, dissemination, and archiving of research topics and results in the field of text generation. It maintains a website that is rich with up-to-date information about natural language generation. The site includes numerous resources, including links to proceedings from the natural language generation workshops and conferences, information on upcoming conferences related to natural language generation, employment opportunities, and a who's who in natural language generation. There is one natural language generation specific meeting that occurs biannually called the International Natural Language Generation Conference, the latest meeting of which was in the spring of 2012. According to the conference organizers, the purpose of the conference is to provide the premier forum for the discussion, dissemination, and archiving of research and results in the field of natural language generation. Access to the full proceedings is available online under the ACL Anthology Digital Archive of Research Papers in Computational Linguistics. There is also one natural language generation dedicated workshop that occurs biannually, called the European Workshop on Natural Language Generation. The ENLG Workshop is a biannual series of workshops on natural language generation that has been running since 1987. The papers from the 2011 meeting are available online. Here are a number of PowerPoint presentations and PDF documents, as well as YouTube videos that provide information on natural language generation. The following are a sample of articles which involve the use of natural language generation in the medical domain. User interfaces. What is an interface? Webipedia defines interface as a boundary across which two independent systems meet and act on or communicate with each other. In computer technology, there are several types of interfaces. The user interface includes the keyboard, the mouse, and the menus of a computer system. The user interface allows the user to communicate with the operating system. There are also software interfaces such as the languages and codes that the applications use to communicate with each other and with the hardware. Lastly, there is the hardware interface, which includes the wires, plugs, and sockets that hardware devices use to communicate with each other. In interface designs, user-friendly natural language interfaces are required for their speed and ease of use. However, the challenge lies in understanding the wide varieties of elusive input. Natural language interfaces are an active area of study in the field of natural language processing and computational linguistics. An instinctive and proficient user interface is an important part of the system. To construct interfaces that are easy to learn and easy to use, designers must understand the cognitive aspects of the human and computer interactions. The development of the interface takes into consideration the unique needs of the users. For example, physicians require a clinical approach, whereas coders can understand a more technical user interface. Here are some resources on user interfaces. Machine translation. What is machine learning? The definition of learning from Merriam-Webster is to gain knowledge or understanding of or skill in by study, instruction, or experience. Machine learning equals the learning in machines or computers. Machine learning techniques are algorithms that enable the machines to improve its performance at some task through experience. These tasks include recognition, diagnosis, prediction, planning, data mining, robot control, and so on. Machine translation covers all branches of computational linguistics and language engineering, information extraction systems that make use of machine learning techniques. You need to understand machine learning in order to understand machine translation. In the biomedical world, machine translation is used for information extraction from large databases of medical information by looking for explicit statements about entities and the relationships within the text. The translation process can be described simply as 1. Decoding the meaning of the source text, and 2. Re-encoding this meaning in the target language. Machine translation was first discussed in the 1940s when the newly invented machine called the computer came to be. Machine translation was one of the first applications envisioned for computers. Warren Weaver, in 1949, said, "I have a text in front of me which is written in Russian, but I am going to pretend that it is really written in English, and that it has been coded in some strange symbols. All I need to do is strip off the code in order to retrieve the information contained in the text." When people see text, they understand its meaning. When computers see text, they only get character strings and perhaps some HTML tags. Reference databases are large and may not be user-friendly. Biomedical databases are varied in their level of complexity. Why is machine translation important? Some tasks cannot be defined well except through example. Relationships and correlations can be hidden within large amounts of data. Machine learning and/or data mining may be able to find these relationships. Human designers often produce machines that do not work as well as desired in the environments in which they are used. The amount of knowledge available about certain tasks might be too large for explicit encoding by humans. Environments change over time. New knowledge about tasks is constantly being discovered by humans. It may be difficult to continuously redesign systems by hand. There are many levels of machine learning needed for machine translation to be effective. This diagram demonstrates the broad spectrum of influences that go into developing a machine translation tool. Here's one example of machine translation. Given a database of hundreds of thousands of images, how can users easily find what they want? One idea is that users query databases by image content. For example, the user types in, "Give me images with a waterfall." One approach, someone annotates each image with text on its content. This would be a long and tedious process. The terminology used to describe each image may be ambiguous, and this process relies on the subjective opinion of the person making the annotations. A better approach would be to query by example. The users would give examples of images they want, and a machine translation algorithm would determine what's common among the images and find more images like them. Here's an example of that process. The user requested images of a waterfall, and the machine translation program identified several pictures that have been displayed. Note the feedback section. The feedback process helps adjust the learning of the machine translation program. Feedback is used to narrow down the algorithm used, hence machine learning. How does the system work? For each pixel in the image, extract its color and the colors of its neighbors. These colors and their relative positions in the image are the features the learner uses. A learning algorithm takes examples of what the user wants, produces a hypothesis of what's common among them, and uses it to label new images. See how this could work with medical research? Other applications of machine translation. The Google search engine uses machine translation technologies, such as spelling corrector, grouping together top news stories from various sources, analyzing data from over 3 billion web pages to improve search results, and analyzing which search results are the most relevant. Spam Assassin for filtering spam email, data mining programs for analyzing medical records to automate diagnosis, intrusion detection for computer security, speech recognition or face recognition, biological sequence analysis. These are just some, but not all, of the current uses of machine translation technology. Machine translation technology started as a field that was mainly for research purposes, with a few niche applications. Now applications are widely used. Machine translation technology can find patterns in data that humans cannot. Have you used machine translation technology recently? Do you have an iPhone? Spoken with Siri lately? Have you completed an internet search looking for information on a particular topic? Did you find this information using a Boolean search engine? With the vast amounts of data overtaking our world, there is a need to develop even more sophisticated machine translation programs. Some concluding questions about natural language processing. How can we, as clinical informaticists, integrate clinical expertise into developing interfaces that will assist providers to be more adept at achieving successful patient outcomes? How can we, as clinical informaticists, provide the necessary support and education for providers to improve care using natural language processing? How can we, as clinicians and clinical informaticists, aid in developing extraction tools in order to pull only the best information and thereby avoid information overload? How can user-friendly interfaces be combined with information retrieval tools to organize information in a clear, efficient manner for providers? Thank you for watching our presentation.